Welcome, folks. Today we're going to perform a permanent magnet simulation of two permanent magnets that are facing towards each other. And then we're going to do one where the permanent magnets are facing in the same direction, so opposite poles. Anyways, the magnetic fields are shown here. These are some screenshot results, but the simulation, the geometry itself is going to be inspired from a geometry that's taken from the Elmer LMAG repository by Elmer. And as we can see here in the repository, there's a list of files and folders of superconducting coils, inductors, microwave components. But today we're going to focus on bar magnets 3D. You can also download this repository entirely as a zip file and then unload it onto your computer and save it. But if we go to the bar magnets 3D folder, you can see there's a snapshot here of some bar magnet results. These are the dimensions for the magnets, for both of these magnets here, and then some data plotting in which you can write a script for. There's some script examples of how to extract the data. The two files that we're going to focus on is the case.cif file and then the mesh.geo under the mesh subfolder. The mesh.geo is the file that we're going to download so that we can generate a mesh. The mesh.geo is the one we import into Gmesh itself. So I'm going to go ahead and save that here in my folder. And I've saved it previously. I'm just going to go ahead and re-download it for demonstration. And then the CIF file contains all the parameters that we need. Well, I would say it's more like a list of recommended parameters that were generated from whoever created this original simulation. But for our purposes, we will use many of the default values that come with Elmer, and then we'll also use some of our own parameters as well, including some of the post-processing. And I'll show you what that looks like here in a bit. And here's some notes for you. You can screenshot this if you'd like. But the two primary tools that you would need to use Elmer successfully is Gmesh, and you also have Elmer VTK. So these tools are free. All of these tools listed here are free on open source. The thing is, Elmer VTK is a post-processing tool that comes with Elmer. There's no need to download that separately. And then, on the other hand, Gmesh, you'd have to download that separately. ParaView, you have to download it separately. It is also, ParaView in itself is used for post-processing, and it's an optional tool. It's good to have. As far as using Gmesh is concerned, the primary goal of that is to generate some mesh file that we can import into Elmer. For 3D geometry meshing, in our case, we need to use the merge tool, and the file that we're going to merge or that we're going to import using the merge tool has to be IGES. I would say it's preferred because I guess in some cases for some folks, STL works to some extent. But for me, for some reason, STL doesn't work. But IGES is something that's foolproof. If you get an IGES format of a 3D model, you can import that, and it'll allow you to generate a volumetric 3D mesh in Gmesh, which is what you want for a 3D simulation in Elmer. That was a long-winded statement. Anyways, the refine by splitting tool is another one to focus on, and that pretty much behaves like a subdivision tool. It allows you to split up the mesh into smaller pieces. And then the 3D meshing tool, of course, is the one that creates the 3D mesh itself. So, all right. And here are some general settings that you want to focus on as far as permanent magnet simulations is concerned. But I would say these are just recommendations, my personal recommendations. And if you want to do animations of the simulation, then you would change the simulation type into a transient type. The default option is called a steady state, which is more like a single frame or a single shot, like a one go, single frame of the simulation result. But the SIF changes we need to change, in our case, is the active solver. Okay, so let's go ahead and open Gmesh. I have it here in dark mode because that's my personal preference. And what we're going to do is just show you, well, I'm going to show you how the dark mode is activated in case you want to know. But to import the file, we're just going to go ahead and open and then locate the geo file that we have downloaded from the GitHub. And this is the geometry file that's going to be converted into a mesh. So you should see a box that looks like this. And if we focus in on what's inside of this box, you'll see these two bar magnet geometries, which have not been turned into a mesh yet, but we're going to get that too. We're going to get to that here in a moment. So if we expand the tree under the mesh options and we find the 3D tool, if we click on this, it will allow us to generate the 3D mesh. And then it'll take a moment here, wait a few seconds, you should see what looks like a big old spider web in 3D. See all these little mesh structures going everywhere. Looks really nice. Very neat, especially with the dark background. All right. And then there are some other options that you can consider, like the merge by splitting tool. If you were to click on this, then it would increase the density of this mesh. It will become more refined in some sense. So what we need to do now is export this mesh, and we need to give it a name and then manually add the extension .msh. Once that's done, then we can save that in whatever folder. And then we can save it using the default option, which is version 4 ASCII, and then it's fine. Press OK. Now we can proceed with closing Gmesh, and then we can start to upload the mesh file into Elmer. Okay. Let's proceed. We'll open Elmer here. Everything's blank, that's good. Now we're going to go ahead and go to File, the File tab, and then we're going to go ahead and just go directly to open the mesh itself. So just going to press on Open, and then locate the mesh file, the .msh file, and then press on Open. The mesh should load. If it's a bigger mesh, then it'll take a few seconds to load. And you should be able to see the geometries on the inside. So here are the two bar magnets that we are interested in. Now we need to define the equations, the critical equations. In this case, we're going to look for magnetodynamic equations, or otherwise known as the solvers. So once we go into the definitions here, we can double check by clicking on this EDF tree, and then as we expand this list under attributes, you should see that there is no magnetodynamic solver available by default. So we need to add that by going to append, and then after that we can dig into the Elmer GUI folder where it's installed on your computer, and then look for a bunch of XML files here, and then magnetodynamics. Magnetodynamics is applicable to the 3D simulation, so we'll click on that one. And if we go back to the list here again, once more, collapse it and then expand the EDF tree, we should see MgDyn some MgDyn and variations of that solver here. That's what we're going to use. Now we are ready to actually import those equations. So first thing we're going to do is go to Model and then click on Equation. Well, scroll down to Equation, click on Add, and now we should be able to see some options here. The MgDyn tab should show up. We'll set that as active, set this as active, and then set it as the first priority, and just name it MgDyn. This is a custom name. You can name it whatever you'd like, but in my case I put MgDyn. And then we need to click on Add New, Add, and then New, and then now we're going to add the post-processing solver, and then we'll leave the priority blank. And we'll just give it a name as MgDyn Post. And then we'll go ahead and click Add, and then press OK to close it. And then press OK again on the other window to close that one. That's good. Now we can see both equations. And then the other thing we need to double check for is the solver settings on the post processing. So MgDyn Post, under that tab, you should click on Edit Solver Settings. That's the other thing I forgot to add. Okay, so if we expand this solver control, we should click on solver specific options and then check the box that says calculate magnetic field strength. That's what we would be interested in seeing as well. So go ahead and apply that, and then update, and then press OK. Okay, that's good. So all the equations are set and ready to go. Now the next thing we need to do is add materials. So we need 3 materials. The first one is fairly easy. It's the air. So we go to the MgDyn tab, and then we need to give it a name and call it air. This one I say is easy because we just set the relative permeability to a value of 1. It's almost always 1 for these kind of simulations. Well, at least for magnetic simulations. And then we just add that, and then press New to add another material. So this next material we're going to add is going to be the MgDyn is under the MgDyn tab again. This is going to be the first magnetic material for the first magnet. So we're going to call it magnet 1. Then I'm going to go up here again, and the relative permeability and the magnetization value, we can double check. We'll go to the CIF file on the repository and then look at case.cif. If we scroll down to the materials section of this script, material 1, you can see here there are some values that were used for the air parameters. Some of these are default values, others are put on there, but I would say the critical one is the relative permeability. That's the most important one. So we'll keep that, and then the rest we'll keep it as blank. For material 2, which is the first magnet, this one we're going to go ahead and copy this long value, which is the permeability. The permittivity is 1, so we'll go ahead and we'll just memorize that. And the magnetization value for 1, 2, and 3 it corresponds to X, Y, and Z. The X-axis, the Y-axis, and the Z-axis. We're going to remember these values, and you can see here that for magnetization 1, the X-axis is 890 e to the third. This is an E notation. And then the other values are just 0. So if we memorize what this is, it's the same for the other magnetic material as far as the permittivity and the permeability. And then the magnetization in the Y direction, which is magnetization 1, it's just a negative value. So 890 e to the third. negative 890 e to the third, which means that these two magnets are, the poles of these two magnets are facing towards each other. That's what it means. And then for the boundary condition, we just remember that it says external BC as far as the name, and then AVE, a value of real 0. Now, if we memorize all of that, we go to the settings and we set the magnet 1 parameters. Relative permittivity, we can set it to 1. Relative permeability is a long number that we copied. And the magnetization should be 890 e to the third, otherwise known as 8.9 e to the fifth. It's the same thing. We'll just use the real value. And then the magnetization value for the Y and the Z direction is just 0. There you go. We'll add that and then make a new magnetic material for the other magnet. Well, it's pretty much the same. It's just we're going to change the magnetization direction so that the two magnets are going to be facing towards each other. That's all. So let's go ahead and change the value of the permeability. Make sure that's the same. Yep. And then the permittivity is 1, like before. And then we're going to use the real value of negative 8.9 e to the fifth for the X direction. And then the Y direction and the Z, 0, of course. It's the same as the other one, except for the direction, like I said. And then we'll call this magnet number 2. We'll add that, and then we'll press OK. And then we'll press OK on that one as well, and press OK on this one. That's good to go. So now we have set the material values of all the materials that we're going to use in this simulation. That's good. And we can skip the body force. We can skip the initial conditions. That's not needed. You can add that if you want. It's optional. The boundary condition, now we're going to add this one. If we recall from memory, the value we need to change, which is under MgDyn tab, is AVE, the AVE value. This should be real 0. That's all we need to change. We're just going to go ahead and call it external BC. And then press add, press OK. And now all those values are set. The next thing we need to do is start assigning those values to these body geometries. So we'll assign this to the first equation and assign this to magnet number 1. And then press add. And then we're going to click on the second magnet here, double click on that, and then press equation, MgDyn, and then set the material to magnet number 2. Boom. And then the last one, double click on this outer body, the cube, and this is going to be assigned to MgDyn equation, and then air, the air material, and then add. There you go. So now you should see all these bodies, the 3 bodies that we have assigned values to as far as the parameter is concerned, and the same MgDyn equation. That's good. MgDyn meaning, of course, magnetodynamics equation. That's great. Now we need to assign the external boundary conditions. That's the next step. So let's go ahead and go to Model and then Set Boundary Properties. If we click on Set Boundary Properties, we can click on the last 6 boundaries that are here, and we should see them highlighted on the cube there. And knowing that this is a cube and a cube has 6 sides, we should be able to see that there are 6 highlighted regions or 6 highlighted faces to confirm that we can use these as the external boundaries to cover the entire geometry that we're going to simulate. These are like the outer walls, in other words. So let's start assigning values starting from number 13. Set that to the external boundary condition, and then do the same thing for all the other 5. So there you go. There you go. There you go. And external BC. Boom. Now, all of the values have been assigned to the simulation bodies, to the mesh bodies. That's good. And just to double check, we can actually go through this list and see that all the walls here, or all the faces for the external boundary conditions, have been highlighted. That's good. That's just to confirm. Now, all we need to do is go to SIF and then press generate so they can generate the script for us based off of the parameters that we set. And then go to the SIF file. And now, if we remember, there's something that we need to change on this script, and that is the equations at the very end. These 2 equations need to be combined into one. So I'm going to go to my recommended SIF changes, and then I'm going to combine this into one. I'm going to go ahead and copy this short script here for both solvers. And I'm going to go ahead and just directly paste this into the SIF script that's been generated in Elmer. So just going to go up here and then replace those 2 equations there, and then put both solvers under one short little script. Yeah, and then from here, all we have to do is double check everything else should be good to go. Then we can just press the play button here, this green play button, and it will run the script. And then when the script is running, that means the solver is ready to go. But this will allow us to save a project, so we just need to select a folder where the results are going to be saved in order for the simulation to run. And now you'll see this little window pop up showing that the calculation is being performed. It's going to go through the line, go down the line, and then the computation will start. It'll take, I would say, roughly a minute, maybe less than a minute to finish. So we're just going to go ahead and wait. And then we'll also see a nice plot here on the convergence. And you can feel free to fast forward from here if you want. We'll show the results here in a bit once the calculation is completed. And then after that, we'll change the parameters to make sure that the magnets are facing in the same direction. In other words, opposite poles of the magnet facing each other. All right. So computation is running, and then it's actually pretty close to finishing up here. It's going to do the post-processing. Okay, so we are back. It's finished a little earlier than I expected. But this is the convergence plot. You should be able to see 2 different lines for the MgDyn and MgDyn post. We'll go ahead and close that, and then we'll go ahead and close this window as well. And then now we can look at the post-processing results. We'll go directly to run and then start Elmer VTK. This is the solver. You'll see initially a blue cube. This is the surface of the external boundary condition box. We'll go ahead and unclick the surface, and then we'll zoom into where the bar magnet geometry is outlined. And what we need to do now is assign a color to the vector and then apply. And some warning will show up saying that there's no vectors yet. So we'll go ahead and activate the value for the magnetic field strength, and then we'll unclick the scale by magnitude so that the magnet vectors will show. And then we'll also assign that to some flux density. And then we'll change the length to 1 so that we can show the arrows, more arrows coming out from the magnet, representing the vector fields or the magnetic fields. Or should I say, it behaves like a magnetic field line. It follows the magnetic field lines. The arrows follow the magnetic field lines coming from the magnet. Sorry, there's some hair in my eye. Anyways, you can see the magnetic field lines here represented by these vector fields. And as I mentioned, both of the magnets are facing the poles. The same poles are facing towards each other, so you can see the magnetic field here is opposing each other. So we can also record this value. We can take a snapshot here. Have a look around. Excellent. We'll go ahead and save this picture as, and this will be a snapshot of our results. We'll call it opposing magnetic or opposing magnets. There you go. And I will save one more view of the permanent magnet here. Again, opposing magnets, number 2. So now that that's done and we can see those magnets doing their thing, we can go ahead and go back into the script, the SIF script, scroll down and then edit, and we'll go down to the material section. And the only thing we need to change here in order to make the opposite poles of the magnet face towards each other is to change the magnetization so that they are both facing the same direction. If the poles of the magnet are facing the same direction, like I said, that means that the opposite poles of each end of the magnet is facing each other. That's what it means. And we'll see the result here in a moment. So I'll go ahead and just directly run the script. It will save it by itself. And then the computation will run. It'll take another minute or so. And then we'll look at the results. And I'll show you that the magnetic field lines show that the magnets are attracting towards each other. They're attracting magnetic fields. All right. So we can see some computation results. That's good. We are about halfway through. We got a couple of more minutes to go, then after that we'll be ready to go. Alright, so the MgDyn calculation's done, and now it's about to do the post-processing. There we go. Now we get a nice convergence plot. Alright, then you get some notifications. We can close these windows and then have another peek at the magnetic fields under the Start Elmer VTK. And there we go. Now we can see the magnetic fields are attracting towards each other rather than repelling each other or opposing each other. Check this out. So I'm going to go ahead and save this view. The scale bar, I can deal with that later. That's fine. Did I say scale bar? The bar that's on the bottom for representing the magnetic field flux. The flux density and the magnetic field strength. I'll change that later. But for now, we can look at this up close view of the magnetic fields attracting towards each other. Look at that. It's pretty good. I'm going to take a couple more snapshots here of this beautiful simulation. The thing is, I want to make some more magnet simulations. I'll be doing pseudo Hilbert curve magnet simulation from scratch. I'm not going to use the GitHub tutorial this time. The GitHub tutorial this time around was just so that you have some files to reference from an existing GitHub. But I'll make some examples in another video showing one where you can create a 3D geometry in Fusion 360, or, well, I guess it's not called Fusion 360 anymore, it's just called Fusion. Autodesk Fusion. But I'll create the geometry there and then we'll export it as an IGES file, put it into Gmesh, do the same thing, same process, and then we'll define it with some powerful magnetic geometries. Okay, that's good. So I went ahead and adjusted the magnetic flux density here. And here's a nice view of the permanent magnets attracting towards each other. I'll go ahead and save this view again. There's a lot of really nice views here. Excellent. Well, folks, it was great having you here. Have a great day.